I guess we can start. Let me just share my screen. Can you see the presentation in slideshow mode? Guys, hello? Yeah, I would really like if you can unmute your mic and speak because I'm in a different window. I can't read your messages. So it'll really helpful if you can speak it out. Yeah. So hello everyone, I'm Nisha. I'm one of the TAs assigned to you for this course of drug delivery principles and engineering, and this is the first session in the series of 12 weeks. So let's start with it. So basically, this course deals with drug delivery. And have you guys gone through the first week material? Has anybody seen the videos or gone through the transcripts? So that I have an idea of what all concepts you guys have covered, or like, are you directly attending this session? Anybody of you can just unmute your mic and let me know if you have read through gone through the material first.
Yes, ma'am.
Okay, sure. So I'll just give you a recap of what week one consists. It basically starts with pharmacokinetics, which is one of the most important aspects of drug delivery. So pharmacokinetics will is essentially going to tell us, in case we want to treat a disease, what amount of dose should be given, how for how long it should be given, and what are the finer aspects of pharmacokinetics such as bioavailability or elimination and clearance rate. And based on this, for example, if you have a drug and it has its own certain properties such as its solubility, its hydrophobicity, all of that is going to govern how quickly your drug can be eliminated from the body. And based on that, then you can design your dosage regimen in order to have the best possible treatment a disease can have. Next, it also the week one material also covers prodrugs, which are drugs which are modified in such a way that they give you a much more controlled release. They give you a control over the release of how long do you want the drug to be released in the body, at what amount it should be present in the body. One another aspect from week one materials is the biomaterials, which covers several polymers. So biomaterials are basically organic compounds or organic polymers which are used for biological applications. And in the polymers video, you must have gone through several concepts such as molecular weight of the polymers, crystallinity, and based on that, how just give me a minute. So I'll have to keep on flipping in between these two screens to admit whoever is joining next. Yeah, so let's start with few questions. So today I'm going to discuss some old assignments which were already there in this course. And if any of you had attended yesterday's TA session, I think it might be a repetition for you. So you can speak the answers quickly. So let's start with the first question. Can you guys see the question?
Yes, ma'am.
Yeah, so the first question is asking us which two statements are true for pharmacokinetics, and these are few options. I'll give you a minute to go through it, make your answers ready, and when I ask for it, you can just give me off the answer, and then we can discuss. So the options are pharmacokinetic studies help in determining dosage regimens. It helps us understand the drug receptor interaction at the tissue level. Third option is pharmacokinetic studies are used to identify new drug targets. The studies it studies how drugs are absorbed or metabolized throughout the body. Pharmacokinetic studies how diseases spread in a geographical region, and it tells us how drug dissolves in water and diffuses in air. So only two of these statements are true. So does anybody want to give off the answer? No, nobody wants to volunteer.
Is it four, ma'am?
Four is how drugs are absorbed or metabolized throughout the body. Yeah, that is one of the option. And the other one?
First one, ma'am.
Yeah, of course. So pharmacokinetics, if you have gone through the videos, this you might have seen the slide where it essentially is a study of designing a dosage regimen where we are discussing where do we want to give that dose, that is the targeted delivery, how much of the drug do we want, how often do we want to continue it, do we want to give it for a month, for a year, for 5 years, or and how long do we want to keep on giving, like once daily or once a week, once a month, so on. So the right answer is two options. Pharmacokinetic studies help in determining dosage regimens, and the study it how drugs are absorbed or metabolized throughout the body. Any of you have any confusions in the rest of the options? None? Okay. We'll move on towards the next question. So the next question is essentially graph in between aqueous solubility and pH. So the question is aqueous solubility of three drugs were tested at different pH and we have to rank them in increasing order based on their solubilities at pH 6. This is a pretty straightforward question. If you look at the graph carefully, you guys can get the answer. I'll wait for a while and anybody of you wants to volunteer can just unmute the mic and tell me the answer. Anyone wants to say something?
Is it 5, ma'am?
5 is no. So wait. I'll tell you the answer. So first you're right in the first option where in tetracycline where you can see that there is a clear dip in this curve. So naturally tetracycline has the lowest solubility. So we have to rank them in increasing order. So tetracycline will have the least solubility at pH 6, followed by if you see this one that is indomethacin, and then there will be chlorpromazine. So I think you just confused in between the last two. Otherwise you were right. Did you get that?
Yes, ma'am.
Yeah. Anybody else has any doubts in this? Okay, we'll move on towards the next question. So this question asks us what particles of what size can be excreted by kidneys. So if you guys have gone through the material where it's discussed, the elimination routes of the drug is discussed, you can answer this. So these are your options. So anybody wants to volunteer? If you guys want to read, I can wait for a while. Anyone knows the answer?
Is it 3, ma'am? 10 to 100 nanometer.
Okay, so I'll first discuss what this concept is and then we can look at the answer again. So this is the glomerular filtration membrane from where all the metabolites in our body gets filtered through the kidneys. So here you can see, I hope you can see my cursor. So this is the gap from where drugs are actually going to be eliminated. So that gap is only for of a dimension of 4 to 11 nanometers. So anything which is higher than 10 nanometers will not be filtered by kidneys as it goes through all these layers. So the question is asking us particles of what size can be excreted by the kidneys. So the answer will be fourth option, that is less than 10 nanometers. So if you say 10 to 100 nanometers, it will be blocked in these layers. So kidney cannot filter those. So this concept becomes important when you want to, let's say, design particles or you want to design nanoparticles which carry your drug and you want those particles to be retained in the body for a longer time. So in case you don't know this concept and you design particles which are, let's say, 5 nanometers, they'll be quickly excreted out of the kidneys and you won't get the therapeutic effect which you want. So the right answer here will be particles of less than 10 nanometer size can be excreted by the kidneys. Any further confusion here? All clear? Okay, sure. If there are no more questions, I can move on towards the next one. Yeah, so next question is, I'll read out the question. An anti-tubercular drug is administered via two paths, inhalation and IV. The alveolar fluid from lungs was collected at different time points. Please explain the large difference in the bioavailability of drugs for different mode of administration. So here we have a graph which is essentially the drug, that is rifabutin, concentration of rifabutin versus the time. So what we can see is uh, this graph is for the inhalation, the concentration at different time points when rifabutin is administered via inhalation route, and the lower one, the circles, is for when rifabutin is administered intravenously. So we can see that there is a clear difference in the bioavailability of these two drugs. So the question is asking us why do we see that? And there are a few options here. You guys can go through the options and then we can discuss which one is the right one. So just for your information, I'll give the bioavailability formula also here, which is essentially a ratio of area under the curve given by any route to the area under the curve given by IV route. So area under the curve is essentially this area. Anybody wants to give it a try? Are you guys there?
Ma'am, is it option three?
Sorry? Can you please repeat?
Third,
Couldn't hear you.
third one.
3. Okay, yeah, that's the right answer. So we'll go through the options one by one. So first one says there was an error while injecting IV and most of it ended up in the interstitial fluid, which doesn't seem logical because we don't know the details of how it was injected. Second is rifabutin is degraded the moment it is injected by IV. Again, we have no details about what the drug, how the drug gets metabolized, so we cannot give this off as the answer. Third is the bioavailability of inhalation route is higher for lungs and is hence reflected from the BAL fluid, which seems probable, but we'll still check out the rest of the options. Difference in AOC is not significant, which is not the right answer because you can see that there is a clear difference in both the area under the curves. Fifth option is the IV route is not a reliable method to calculate concentration of drugs, which is again not the right option because bioavailability is indeed calculated if you have area under the curve for IV method. And last is the inhalation route is not a reliable method to calculate concentration of drugs. Again, the wrong answer. So the right answer is third one. The bioavailability of inhalation route is higher for lungs and is hence reflected from the BL fluid. So as I said, bioavailability is essentially the amount of drug which is available at the therapeutic site. So here they have given it by two different routes. So if you are giving it by inhalation and you collect the alveolar fluid, naturally more drug will be available in that fluid because you have inhaled that drug compared to when it is given intravenously. Because it's given intravenously, the drug is going to flow all over the body because it flows through the bloodstream. As a result, whenever it's given intravenously, it will have lower concentration compared to inhalation. Is this clear?
Yes, ma'am.
Yeah, thank you. Just a minute.
Ma'am, I have a doubt regarding the graph.
Just a minute.
Ma'am, in the
Yeah,
IV route,
yeah.
uh, like before reaching the peak, there's a line going from zero to the peak in
From
the
here to
IV
here,
route.
you're saying.
Yes,
Yes.
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 And in the lungs route,
Yeah.
the inhalation route, there's no there's no slope going from zero to peak.
Right. Right.
Why is that so?
Okay, so I can try answering this as best as I can. So when you're giving any drug intravenously, that is a very instantaneous action. Once you inject anything in the blood, it's going to flow very fast, and that will be reflected in any part of, let's say you take blood from the arm, or here they are collecting it from the alveolar fluid. So the drug will immediately be reflected in that particular place. Compared to inhalation, when you are inhaling any drug, that has to pass through a more longer route, because you are going to inhale it through your nose. It will then pass through your trachea, and then will go to your lungs, and then will go to alveolus, and then it will be reflected in the alveolar fluid. So the route taken for drug via inhalation is longer. That's why you don't see anything when they take it in the at the zero time point. Later on, if you're taking it, if you're checking the alveolar fluid, there most of the drug will be accumulated. So it shows a very high peak for this, and from there, as the time goes on, it will go on reducing. Compared to that, for IV, at zero time point, when nothing is there, you won't see any drug, but immediately after that, you'll see a high peak. Is this making sense?
Yes, ma'am. Yes, ma'am.
Yeah.
Thank you.
Yeah. So this route, so whatever you see for inhalation, we also observe it for if you inject your drug subcutaneously or intramuscularly as well. But for IV, it will always be instantaneous. Okay. Any other doubts?
Ma'am, as I actually I joined late,
Okay.
I actually wanted to review the second question again.
Let me go back to the second question. This one?
Yes, ma'am.
Yeah. You had any doubt in this?
Yes, ma'am. Like, I didn't understand how to like we can rank the solubility.
Oh, okay.
You
So
know,
this is just a straightforward question. You don't have to calculate anything just because it's a graph. So here you can see that whatever is lowest at 6, so they've asked us the increasing order of solubilities. So whatever solubility you see at 6, definitely this is the lowest. So your tetracycline will have the lowest solubility at pH 6. Next graph, if you see at this particular point, is this. That is the indomethacin. And further, if you wait. Further, if you'll go higher than this, then it is chlorpromazine. So if you rank the solubilities at pH 6, tetracycline will have the least solubility. Then indomethacin has a little higher than tetracycline. And then the last drug, chlorpromazine, has the highest solubility at 6.
okay, ma'am.
Yeah,
Thank you.
it's just a question where you look at the graph. No calculations
Okay.
involved.
Okay. Thank you, ma'am.
Yeah, welcome. So if anybody has any doubts or wants to contribute to the discussion, you can unmute your mic and speak, because I can't look at the chat section. Okay, so we'll move on towards the next question. Next question is, which of the following will have higher partition coefficient? So if you guys have gone through the material, you'll know what a partition coefficient is. So these are few of the options. I'll first wait for you to guess the answer. If not, we can discuss the concept of partition coefficient.
First option.
Yeah, that's right. So partition coefficient is essentially a ratio of the amount of drug in the oil phase to the amount of drug in the water phase. So, so whenever you want to, so partition coefficient is an inherent quality or inherent property of a drug. So whenever you want to calculate this, what you do is you take an oil phase, which can be an organic solvent, to a water phase, and then you put your drug in that. After a while, it will partition in between these two phases depending on its solubility, either in the oil phase or in the water phase. So partition coefficient for those drugs will be higher who have a longer carbon chain, because they'll be more hydrophobic in nature, and they'll dissolve in the oil phase more compared to the water. So the question is asking us which will have higher partition coefficient. Whoever will have a higher solubility in the oil phase will have a higher partition coefficient. From the given options, you can clearly see that the first compound has a lot of carbon chains to it, carbons molecules in it. As a result of it, it will be more hydrophobic and it will have the highest partition coefficient. Making sense? If you guys have any doubts, you can just unmute the mic and ask. Okay, so I'll move on towards the next question. Next question again deals with the concept of partition coefficient. Here we are asked which of the two statements are false for partition coefficient. And these are a few of the options. So you guys can take your time reading this, think over it, and then let me know the answer.
Option 4. I'm Sujata Group.
Option 3, ma'am. Option 3, ma'am.
Okay, someone said option 4, that is the lower the polarity of drug, higher the lipid water partition coefficient. And somebody said option 3, higher the lipid water partition coefficient, lower is the rate of transfer across the membrane. So fourth is the right option, but we need one more statement. So you guys can give it another try. One of the answers is lower the polarity of drug, higher the lipid water partition coefficient. We'll discuss how third is not an answer, but you can give another try.
And option 2.
Yeah, so option 2 is right. So let's look at partition coefficient again. As I said, higher uh, the for the drugs whose partition coefficient is higher, they are more hydrophobic in nature. As a result of which, they'll have low polarity. Low polarity meaning they'll be more they can dissolve in water quickly. So this fourth option. So we want to see which of the statements are false. So lower the polarity of drug, higher the lipid water partition coefficient, which is false because if you have higher partition coefficient, naturally your drug is going to be non-polar. That is, it's going to have lower polarity. And the second option, the higher the lipid water coefficient, the greater the rate of transfer across the membrane. Just a minute. I hope I. Yeah, sorry. So whoever said the third option is the right answer was actually right. My bad. So it's asking us the false statements. So higher the lipid water coefficient, it will have higher the rate across the membrane because it's more hydrophobic in nature, and we know that the cell membrane has lipid molecules attached to it, so it is also hydrophobic, comparatively hydrophobic in nature. So more the partition coefficient, more will be the rate of transfer across the membrane. So the option 2 is actually the correct, but the question is asking us which are the statements which are false. So the false statements are uh, low, yeah, the higher the lipid water partition coefficient, lower is the rate of transfer. And the fifth option, higher the polarity of drug, higher the lipid water partition coefficient, is false. I'm thinking you guys must be confused in this. Is there any confusion? We can go over this again. Anybody there? If there is any confusion in this, you can ask me again.
Ma'am, can you tell me about polarity? What does it mean? I cannot understand it.
Okay, so polarity of a drug is how polar that drug is. It means, let's say you have NaCl, and if you put NaCl in water, it is going to readily break down into Na plus and Cl minus. So it will have two poles. So that means it will easily be dissolved in water. So polarity essentially means that it will be more readily dissolvable in water.
Okay, ma'am. Thank you, ma'am.
Yeah. So the last option says the higher the polarity of drug, higher the lipid water partition coefficient, which is not the case because if it's more readily dissolvable in water, its partition coefficient should be lower.
Okay, ma'am, clear.
Yeah. Give me a minute before we move on towards the next question. Okay, so the next question is which of the following two statements are true for bioavailability? And these are few of the options. You can take your time in reading this and let me know the answer. So this is the formula for bioavailability.
The last option is true.
Yes, that is one of the answers. We need one more statement to answer the question correctly.
Second option.
It can be determined by calculation. Yes, so these are the two right answers. So the concept of bioavailability, as we already discussed, is essentially deals with how much amount of drug is available at the particular site for its therapeutic effect. Let's go over the options one by one to make it more clear. First option is it refers to how much drug is available in chaos, which is definitely not totally illogical. Next is it can be determined by calculating area under the curve by plotting the serum concentration of drug over time, which we saw in the previous question. We had a graph which was area under the curve for the serum concentrations versus time. So that's how we calculate bioavailability. Next is it does not depend on route of drug administration, which is also false because in the previous question we saw that depending on how you are administering a drug will change how much drug is available. So that is again a false statement. Fourth is it refers to the amount of drug that is lost in first pass metabolism. That has nothing to do with bioavailability. That is a different concept. Fifth is it does not depend on drug physicochemical properties, which is also false because it will depend on the drug physicochemical properties. Depending on, so it depends on what are the properties of the drug as well as the route of administration. And last is bioavailability is considered 100% when the drugs are administered intravenously, because when you give a drug intravenously, it will all of that entire drug is available for you for to act through the bloodstream, and as a result it will have more the highest concentration in serum. So these two options are correct. If you guys have any doubt, you can ask away. Any doubts in this?
No, ma'am.
Okay, so I'll move on towards the next question. So this is a numerical. I'll read through it slowly. A drug has half-life of 30 minutes in its native form. PEG is conjugated to the drug to improve its pharmacokinetics, and the modified drug is injected intravenously with an initial plasma concentration of 1 mg per ml. After 12 hours, the concentration of the drug in serum is 0.5 mg per ml. We have to calculate the change in half-life of the drug after modification, assuming first order kinetics of elimination, and we have to give our answers in the unit of hours. So you guys can take a paper, pen, start solving it, and let me know when you have the answer. After a while, we'll discuss the solution one by one. Does anybody have the answer? So sorry, I couldn't display this before. So this is the equation for the first order kinetics of elimination. You can take help from this. Are you able to solve it? Shall we start discussing the solution?
Is it 6 hours?
Uh, I think you are somewhere halfway there. I think the answer is 12 hours. We'll discuss the solution. Anybody else has gotten the right answer? Okay, we'll discuss the solution.
11.99, almost 12 hours.
Yeah, you're right. So usually the answer will be given in a range. So whenever you guys will be solving it, this solving such questions in an exam, you'll always have a range. So let's say so it can fall anywhere in between this range. Your answer can range from 11.2 to 11.9 anywhere, depending on. So I've used this on a calculator, so that's why it's somewhere near 12. So we'll discuss the solution step by step. So first of all, let's list out whatever is given. So the initial drug plasma concentration is 1 mg per ml and the final is 0.5 mg per ml. So I'm considering C naught as the initial, CT as the final concentration. The time given is 12 hours. So in 12 hours, it has fallen from 1 to 0.5. Next, so we have this. So to solve this completely, we have to find the elimination constant first, because if you see this equation here, we have CT, we have C naught, we have time as well. We just have to calculate this first, the K elimination constant. So if you put this in an equation and you solve it, you'll get this as your uh, K elimination. Further, we have to calculate the new what is it? New half-life. So for the half-life expression, your CT will be half of C naught. Since half of the drug has already been eliminated, that is a definition of half-life of any drug, where half of the concentration of initial drug is already gone. So your CT will be 0.5 C naught, and so you put that again in the same expression, where now you have the value of K and you just have to calculate T half. If you solve this expression, you will get 12 hours. Is it clear? Any doubts? So this is the longer method of arriving at an answer. But if you guys have read the question carefully, the initial concentration was 1 mg per ml and the final is 0.5 mg per ml, which is already half of the initial concentration. And they have already given us that in 12 hours, this is the concentration that is the concentration is already reducing by half. So if you have even read the question carefully, you could have directly written 12 hours. But in case sometimes it happens when you are in an exam and you are getting confused with all of these values, some of these values are not even of any use. Let's say the drug half-life in its native form, we have not used it anywhere. So this was totally irrelevant, but it's just given so that you get confused more. So in an exam, you'll have very less time to solve these questions. So it's better if you smartly arrive at this answer. Read the question very carefully. You don't even have to solve this. You can directly guess the answer. But if there is another question which deals with something like elimination constant or calculate how much amount of drug will be left, if they give you the initial value, they give you the elimination constant, and they give you the time, you can easily calculate how much amount will be left. So the solution will help there. So if you guys have any doubts, you can ask. Is the solution clear? Shall I move on towards the next question? You guys can hear me, right?
Yes, ma'am.
Hello.
Yes, ma'am.
Yeah.
Madam, I have
Yes.
a doubt.
Yes.
So here the question is calculate the change in the half-life of a drug
Right.
modification assuming first. So change we have to calculate. So initially it was 30 minutes and now it has been 12 hours.
Okay. Okay.
So do
So
we
so
need to report the answer as the change is 11 hours and 30 minutes like that?
yeah. So even if you do that, so your answer will be 11.5. Right?
Yes.
Yes. So that
Yes.
is also an accepted answer. So some of you might see this question as you have to calculate the new uh,
Yes.
half life, and some,
Modified.
yeah. So that is why you have this range. Even if you get 11.5, it's still a right answer, and even if you get 12 hours, it's still a right answer.
Thank you.
Yeah, so this question essentially tells us that, so let's say you had a drug and you just gave it, and so its half life is 30 minutes. It means it's going to be eliminated from the body very quickly. Compared to that, if you want the same drug and now you want it to last in the body for longer, because instead of taking it, let's say, every morning and evening, now you want your patients to take it only once in 2 days. So in that case, if you conjugate your drug with PEG, which is one of the polymers, polyethylene glycol, that will reduce its elimination rate, and now the drug lasts in the body for a longer time. So this is just an example to understand this concept, where you can modify the drugs using polymers and then design effective treatment regimens. So no more doubts. I'll move on towards the next question. Okay, so let's read the next question. A polymer is made up of the following composition, where we have 10 moles of molecular weight of 40,000, 15 moles with molecular weight of 45,000, and 5 moles with molecular weight of 50,000. What is the polydispersity index of the polymer? So, do you guys know about the concept of polydispersity index? If you have read the material and you already know the formula, I can display that. If you know how to solve it, you guys can go ahead, solve it, and then let me know the answer. If not, we'll discuss it after a few minutes. Let me know when you have calculated everything and you have the final answer. So polydispersity index is just a ratio of MW by Mn.
Answer is 1.
Yeah, the answer is 1. I'll just display the solution. So first of all, the concept of polydispersity index, we have this because whenever a polymer is synthesized, it usually has a lot of heterogeneity. It has a lot of change of different molecular weights, like we can see in this example, where 10 moles of different weight, few chains are of different weight. So as a result of which, the polymer itself is very polydispersed. It does not have a single molecular weight. So to characterize polymers like this, we have this concept of polydispersity index. Now that is a ratio of Mw by Mn, where Mw is the weight fraction of the polymer, and Mn is the mole fraction of the polymer. So pretty straightforward formula, where Mn is just the summation of the moles to its when it's multiplied by its molecular weight. So because you have 10 moles of 40,000 weight, 15 moles of 45,000, and 5 moles of 50,000, you just take an average of these. You multiply them and you take an average by dividing it with the total number of moles. Then you will get a value which is something like 44166, because I've used all of us must be using different calculators, so this value can vary a bit. Next, we have this MW, that is the weight fraction of polymer. Again, a straightforward formula. You take the number of moles, you multiply it with the square of the molecular weight, and then you divide this to get the average. There again, you will get some value, and then you take a ratio of these two. So your answer should be somewhere around 1. So it cannot be less than 1, because your MW in all the polymers will always be more than your Mn, because it's the weight fraction. So yeah, MW will always be greater than your Mn. So your polydispersity index will always be higher than 1 or higher than 1. Although the range here says your answer can be somewhere in between 0.7 to 1.3, that is just to admit the uh, because different calculators can show you different values. It should ideally be 1 or higher than 1. I'm not sure if you guys are allowed calculators in the exam. I think not. You have to solve it manually. I am not sure. Any doubts in this question? Shall I go ahead?
Yes.
Yeah. Okay, so this is the last question for the assignment. A drug A is injected into a patient. The rate of elimination of A is 25 gram per minute and its plasma concentration is 5 mg per ml. What is the rate of clearance of the drug from the body in liter per minute? Assume that the drug distributes in the total body water. So you have all the values. You guys must be knowing the formula. If not, I'll display it on the screen and you just have to calculate and let me know the answer. I'll wait for a few minutes for your response.
Point 0.005 liter per minute.
Sorry, can you please repeat?
0.005 liter per minute.
0.005. I think you did not look at the unit conversion. Did you take that in account? Because
Yes, ma'am, I take it in plan.
yeah, the answer should be 5.
5
Yeah.
liters per minute, ma'am. 5 liters per minute.
Right. You are right. So whoever answered points, I cannot see your name, I think you messed up with some of the units, I guess, because
5 liters per minute.
yes, you're right. You're right. I'm
Oh,
talking
thank you,
to the
ma'am.
previous person who spoke. So let's first list out whatever is given. We have rate of elimination in 25 gram per minute. We have plasma concentration at 5 mg per ml, and we just have to calculate the rate of clearance, which is nothing but the ratio of rate of elimination to the plasma concentration. So here, if you see, your numerator is in grams, your denominator is in mg. So you have to. So I here have converted gram to mg, and then since this is in ml, we have to convert it to liter. I have converted ml to liter. So initially it should be 10 raised to minus 3, which then goes towards the numerator, becomes 10 raised to 3. That just gets cut down. And your final answer should be 5 liter per minute. Is this clear? Is there any confusion? Anybody has any doubt in this? Yeah, so this was the last question for a discussion today. Since some of you joined late, I'll just go over the questions once again. If you guys feel this is a repetition, uh, that's all I have for today. So I'll just quickly go through the questions. If anybody has any doubt, just stop me there and we can discuss the concept further. So first question is, which two statements are true for pharmacokinetics? So pharmacokinetics essentially deals with the designing a dosage regimen, which includes points such as where do we want to give the drug in the body, how much amount is going to be administered at once, how we are going to administer it, that is the route of administration, how often, meaning the frequency, is it going to be daily, is it going to be weekly, monthly, and how long is this treatment going to last for. So pharmacokinetics essentially helps us in determining the dosage regimens, and it also tells us how drugs are absorbed or metabolized throughout the body, which includes the concepts of clearance as well as elimination rate. So these are the two right answers. Next question was asking us, it's a graph of aqueous solubility versus pH, and it is asking us to rank the increasing order of solubilities at pH 6, where here you just have to look at the graph carefully and see that whoever has the lowest, so it's an increasing order, pay attention to that question. So the least soluble will be tetracycline, slightly more solubility will be for endomethacin, and then last chlorpromazine with the highest solubility. So that's the answer. In the next question, we were asked particles of what size can be excreted by kidneys. This is a purely theoretical question where we don't have to deal with any concept. You just have to know that some of the architecture of how things get cleared from kidneys. So this is the last barrier where things in between 4 to 11 nanometers can be cleared. So as the question is what size can be cleared by the kidneys, the right answer is less than 10 nanometers. Next question essentially gave us a graph of bioavailability, and it is asking us that a particular drug is administered via two different paths, inhalations and IV. And the authors have collected alveolar fluid from lungs at different time points. And this is how the graph looks like. So the question is asking us, why is there such a large difference in between the bioavailability for inhalation and versus the intravenous route? So the right answer is because bioavailability of inhalation route is higher for lungs, and that is what is reflected in the alveolar fluid. So this question tells us that your bioavailability is not going to be constant for a particular drug. It is going to change based on the way you are administering it, where you are checking the concentration of that particular drug, and also on the properties of the drug. Next question is, which of the following will have higher partition coefficient? As I said, partition coefficient is the ratio of the solubility of the drug in oil phase to the solubility of drug in water phase. So naturally, whichever has higher hydrophobicity will have higher partition coefficient. So the answer here is the first option. Next question is, which two statements are false for partition coefficient? Had a bit of confusion here because of the question. So the false options are, the higher the lipid water partition coefficient, the lower is the rate of transfer across the membrane, which is false because more the partition coefficient, more will be the rate of transfer since your membrane is also hydrophobic. The next false option is, higher the polarity of drug, higher is the lipid water partition coefficient, which is also false because more polar the drug is, more it will be readily dissolvable in water, and it should ideally have a lower partition coefficient. Next is, we had this question of which of the following two statements are true for bioavailability. So the right options are, it can be determined by calculating area under the curve by plotting serum concentration of drug versus time, and bioavailability is considered 100% when the drugs are administered intravenously. Next we had, is anybody trying to say something? I can hear. Anybody has doubt? Okay, yeah. So next was a numerical where we were given few values and we were asked the T half. That is the, so there is a particular drug which has been modified and they are asking us what will be the new half-life or the change in the half-life. So you should be knowing the formula for the first order kinetics, which is this. And then if you just put in the values, you can first calculate the K elimination constant and then later on use the same formula to calculate the new half-life. Then there was one question of polydispersity index, where we were given certain values of how dispersed the, so we have to calculate how dispersed is the polymer. So this is also straightforward numerical where you should be knowing this formula. Mn is the mole fraction of polymer and Mw is the weight fraction. So polydispersity index is nothing but a ratio of Mw by Mn. Since you have all the values, you just have to put it in the formula, get these two values first and then take a ratio. So your answer should be somewhere around 1. And then the last question was, a drug A is injected into a patient and we have been given the rate of elimination and the plasma concentration of the drug, and we are asked what is the rate of clearance, how quickly the drug will be cleared out from the body. So again, you have a straightforward formula. Clearance is rate of elimination divided by the plasma concentration. Please pay attention to the units and what is the answer is supposed to be in which unit. So after the few conversions, you'll just straight away arrive at the answer, which is 5 liters per minute. So that's all I have for today's assignment. So this is how your sessions are going to be henceforward. So we'll just discuss one assignment each week. So if you guys have any other problem apart from the assignments, if you have any problem in the lectures, if you have gone through, I can try answering them.
Ma'am,
Yeah.
excuse me, ma'am.
Yes,
Ma'am, when assignment 2 will explain, ma'am.
in the next week. So this is this session is going to happen every week. So every Tuesday I'll be taking a session. So this we have discussed week 1. Next week we'll be discussing week 2.
Okay, week 2 assignments next Tuesday you will discuss, ma'am.
Yes, yes.
Yes, okay, thank you, ma'am.
Yeah. Apart from the assignments, if you guys have any doubt with the concepts, you can let me know and we can try answering that.
Thank you.
Okay, yeah, sure. Thank you. So these assignments, so these are the questions which you can expect in your final exam as well. They'll be somewhat of the same on the same line. So more you solve these assignments, more you'll be ready for the final exam.
Hello, ma'am.
Yes.
Once we submitted our assignments, we can change our answers
No, you
after.
can't. So you can change it until the limit. I think you can submit it more than one time until the deadline.
Okay, up to 8th we have time, ma'am. 8th of
Okay.
this month. So
Okay.
today I have submitted week 1 assignments. If any changes or if anything I need to correct, miss, then I can correct it.
Yeah. I think you can correct it. So right
Again,
now, yeah.
Okay. Again, I must submit. Okay.
Okay. Yeah. You can submit multiple times, but once you have crossed the deadline, you cannot change it.
Okay. Thank you, ma'am.
So if you guys have doubts in the recent assignments as well, we can discuss it in this session. So right now we are discussing the old assignments, the assignments which were already been done last year, I guess. So this is an archive course. So these are the assignments which were floated last year. So we are just discussing those. So let me know if you have any doubts in week 1 material as well. We can take it up in the next session, or else if we have nothing else to discuss for today, you can log off the meeting.
Ma'am, any reference books are there for this subject, ma'am?
There is one drug delivery. Let me get you back to the name in the next session. I can tell you the book which I referred to when I was doing this course. I'll get back
Okay.
to you in the next session, or
Okay.
I can look up right now.
Okay. Thank you, ma'am.
Yeah. If you guys have nothing else to discuss, shall I stop the meeting?
Okay, ma'am. Thank you so much.
Yeah. Thank you.
Okay, ma'am. Thank you.
Thanks. Bye. See you next week.
Thank you, ma'am. Thank you, ma'am.